I want to begin by thanking Louise and the country of Mexico for sending me a wonderful gift. I won't say how many years ago. A treasure, a national treasure. Susanna Lozano, who I was very fortunate to supervise. It's really a great honor to have been her thesis advisor, and I'm so happy that she's now helping this country develop its astronomy. In any case, as Susanna said, I'd like to talk about climate change and sustainable energy. This is just to show that actually climate change arises from a very familiar phenomenon in astronomy. This shows a diagram of what we would see in infrared radiation if we stood outside and looked back at the Earth. We would see an emission, because the Earth is warmed by the sun, that roughly has this shape, but there are big chunks taken out of it. And this is due to what I call greenhouse gases. The primary greenhouse gas is water vapor, but the next most important is carbon dioxide, and then things like methane. Water vapor we cannot do too much about because the atmosphere is open to the ocean. Carbon dioxide is something that we can do about, and we must do something about. So that's the first part of my talk about climate change. I won't discuss this in any more detail, just talk about the consequences. The other is sustainable energy. And by sustainable energy, I include things like nuclear energy, which is part of what we are working on. But that I won't talk about today either. Instead, I'll talk about replacements for fossil fuels that are synthetic in nature, but very similar in spirit to what we use today. And the common link is molten salt. Okay? This is a salt that you can find. It's not table salt, but it's what you will find in toothpaste, etc. If you heat it to a high enough temperature, in this case 900 Celsius, will become a liquid. You can see if you shine a laser beam, it will go through it. And if you cool it back down, it eventually solidifies it into a solid again. So this molten salt plays a central role in the research work that a group of us, which we call ourselves the HX team, that means heat exchanger team, and they involve many people. Some of the astronomers would know the astronomers in here, but they also include engineers and scientists from institutions like Tsinghua University, the National Lab, CSIST, which some of you may know for their work on radio telescopes, and ITRI, which is a applied research lab in Taiwan. So here's the outline of my talk. Climate change, I don't think I need to convince anybody in Mexico, this is really for the Americans in the audience, is real and here. Okay. Then we'll discuss why fossil fuels have become so dominant. And if we want to replace it, we need to understand also its strengths and weaknesses. So why oil is so effective as a transport fuel? Why shale gas is so cheap in the United States today, and other people are rushing toward this source of energy. Why, then, of course, why we need to transition away from fossil fuels with syn fuels. And I'll talk about a process using molten salts, which we call supertorrefaction, to produce solid, liquid, and gaseous synthetic fuels from biomass. Not biochemical ways, but a thermochemical way. If we stop using oil, of course, what does the Mexican economy do? I will suggest some alternative uses of Mexico for Mexican oil, which I hope is not too presumptuous, but I think you have to think about these problems. Finally, I'd like to give a summary, which is well, everybody wants to develop sustainably, many countries. What is the way to develop sustainability? I think there's a golden rule of sustainable development, and that is the principle of zero waste. No matter what you do, you have to tell us what is the waste product. If you have a waste product, you either have to deal with it yourself or you have to pay somebody else to deal with it. Only if we go down this route of principle of zero waste do I think we can ever be developed into a way where we can have a stable, long-lasting civilization. And associated with this is not to be too ambitious. Don't try to solve all the problems of the world forever. Okay, don't look only for the perfect solution. Do not let the perfect be the enemy of the good. Finally, I'd like to dedicate this talk to the memory of Yolanda Gomez, who taught, like my father, that scientists have only one responsibility. And that responsibility is to help create a better future. I think Yolanda's whole life was dedicated to the most important, which is to educate the young. Okay? So I'm very happy to have this occasion to try to continue in that line of teaching by Yolanda, great lady and astronomer. So when we talk about energy, we automatically, immediately bring in economics. And once you bring in economics, because people want to cut corners, we have big impact on the environment. So I'd like to summarize this by quoting a very great economist, John Maynard Keynes of Great Britain. He didn't actually say this. This is kind of my encapsulation of his writings. What he wrote was that for millennia, for thousands of years, until the Industrial Revolution, which was sparked by coal burning, the only way humans made economic progress was to enslave other peoples. Right? You have to keep that in mind. Fossil fuels was not all bad. It did many wonderful things, but it does have one bad consequence. So this plot shows the per capita income in Great Britain where the Industrial Revolution began in 1990 US dollars. So we see for thousands of years, all right, the average income in Great Britain was a few $100s per year. In other words, people lived on $1 or $2 a day. We may think this is remarkable, but I would remind everybody, there are 2 billion people in the world today who live on less than $2 a day. Do not they have rights to aspirations to a better life? That is the fundamental conflict in climate change. So around this time, coincident with the discovery of the New World, people became enslaved in large numbers. And you can see there's a slight rise in the average per capita income. And then came the Industrial Revolution, and things really took off. Why? Because when you have coal and you can make machines do work, it's much more efficient than to have humans do the work. The labor of one person for an hour is equivalent. The energy that is expended is, and the work that you can produce, you can do instead by burning 5 grams of coal at an efficiency of 20% of turning it into work. That's a kind of steam engine efficiency. So that allowed this rapid rise in the per capita income to such a degree that it was no longer profitable to have to use the labor of human hands, and so slavery was abolished. When I say slavery, I don't mean just enslaving people of other races. When people dug up coal in the beginning, the men swung the pickaxes to break loose the coal, and women and children hauled it up out of the mines. Think how tough life must have been, right? So it was a great, great accomplishment to be able to eliminate those forms of social injustice. And of course, we've been on an exponential climb ever since, so that by today, the average per capita income in Great Britain is over $25,000 a year. But, as we all know, this burning of coal and later oil and natural gas has a consequence, and that is the release of greenhouse gases in the atmosphere. Greenhouse gases, like carbon dioxide, act like a blanket, all right, over the Earth in the following sense. If we did not have the Earth's atmosphere, the Earth would still warm up by absorbing sunlight, but it would only reach minus 18 degrees Celsius on the ground as a result of the warming of the sun before it radiated back the infrared radiation. But because we have this blanket, the ground is actually 33 degrees Celsius warmer. That's the greenhouse effect. Okay? And the air, of course, extends up to great heights, up to the stratosphere. At the stratosphere, it receives the light from below, the infrared light, which warms it, but it also is cooled by radiating to a cold and dark universe. So at the stratosphere, at the top of the atmosphere, it's minus 41 degrees C. So that you can get by doing astronomers' calculations. But I just want you here to remember these two numbers. At the ground, on average, both average over seasons, latitude, night and day, the average temperature is 33 minus 18, or 15 degrees Celsius. And at the stratosphere, it's minus 41 plus minus 18, or 59 degrees Celsius. Now, CO2 is 27% of the effect. If you just count how much area was eaten up in the previous slide, 27% of the effect of 33 degrees. So if you multiply those two numbers, you get 9 degrees Celsius. Okay? Now, from this plot, here is carbon dioxide for the past 10,000 years. It came out of the Ice Age, roughly here. Here's the Industrial Revolution, and boom, the CO2 has shot up in the atmosphere from 280 parts per million to 395 parts per million today. So if you just said 280 parts per million is responsible for 9 degrees Celsius warming, how much warming would 395 parts per million be? It would be 12.6 degrees Celsius. That linear scaling is not correct, but nevertheless, the final answer is about right. Okay? In other words, we would expect to see, when things come into equilibrium, a 3.6 degree rise in the temperature, even if we stopped emitting today and just let the Earth come to equilibrium. What we've actually seen is only 0.8 degrees, not 3.6 degrees. That's this difference. And the reason is because it's not in equilibrium. This effect is called global warming. It's like when you're cold at night, you get under the blanket, you don't immediately become warm. You have to first warm up the blanket. That is what we're doing. When we warm up the blanket, we do all sorts of other things, like melt ice, etc. Okay, and that's the reason that we have global warming. It's very simple. So can you trust the astronomers? You don't need to trust the astronomers. The greenhouse effect is everyday experience. So is it 15 degrees on average? Well, Morelia is about an average place on the globe. Spring is kind of the average condition on the Earth. And if you average over day and night, is 15 degrees C a reasonable temperature? I think it is. You can go out and measure it day and night. Well, you have mountains around, so that's higher up. Unfortunately, the mountains aren't high enough here to be able to see this phenomenon. So if you went to look at the highest peak in Mexico, which is above 5,000 meters, you will find that it's snow-capped. The fact that it has snow means that it must be below 0 degrees C. So you went from 15 degrees C to 0 degrees C. What about going higher? Well, you go to an airplane or look at an airplane. What happens? Well, here's a jet plane. It takes in oxygen in the air combined with hydrocarbons and burns it and produces an exhaust, a jet. Okay? Now, when it comes out of the jet, it must be a few hundred degrees C at least, and yet, downstream from that, it quickly becomes this white plume. What is that white plume? If you burn hydrocarbons, the hydrogen will combine with the oxygen to give you water. It's water vapor here, but it quickly mixes with the cold air to become ice crystals. So you see it in this thing. The hot exhaust becomes ice crystals, and the air that's needed to produce this effect in this shorter distance is about 59 C. If you ever take a next airplane ride, ask the pilot or the stewardess, what is the air temperature outside, or read the monitor. It's roughly minus 60 degrees C. So it's a common day experience. The other point, of course, if you burn hydrocarbons, the carbon that is oxidized will become carbon dioxide. Carbon dioxide is a transparent gas in the visible, so we can't see it. And that is part of the problem. Okay? These emissions are causing the blanket to become thicker. Okay? Not only are we not in equilibrium, but we're causing the blanket to become thicker and thicker. And you all know from common experience, if you put on a thick blanket, you get warmer. Not because your metabolism is raised, it's just to push out the same amount of energy, you get warmer. So you get warmer at the bottom. That is the dilemma that faces us. So how large is this warming? Well, say we want to ask, what is the effect on the total amount of rainfall? Rainfall is not something that is predetermined. It's not a single number, as Brett was saying. It's a distribution, right? Tomorrow we have a certain probability of having a certain amount of rain, right? So it's a distribution. Now, so I plotted here, let's say roughly, conceptually, the amount of rain that falls in a year in a given region, from very low amounts to very high amounts. Now, in a normal situation, if we were not worried about climate change, maybe at the beginning of the Industrial Revolution, it might have been this green curve. But today, because we've raised the temperature by about 0.8 degrees, it's shifted. That is, places where there are rain, now the air can hold more moisture, so when it rains, it has more moisture than normal, right? Might be twice as much at this level and more at less level. Notice you have the opposite effect in places which there is not enough rain. That's because when it rains, it goes into the ground, but now the ground is hotter, so the water evaporates more. And if it doesn't really rain there, you get less rain, right? You used to be here, now you're there. This explains the confusion that people have. Okay, why is it that somewhere it gives this effect and elsewhere it's the other effect? It's simply because the total amount of water that the atmosphere can hold is roughly constant, and therefore it's just a shift. It's this whole distribution. The water vapor that goes out here ends up in the East Coast, let's say, as rain. Now, what people then say is it's very hard to see this shift. Right? It's very hard to tell the difference between the red and the green. So many people are not convinced. They should be, especially scientists should realize. When you go out on the tail of a Gaussian, that little shift is a huge thing. So that is the basis of the statement, that extreme events become much more likely. That is, things that were not very likely before, let's say only happens once every 10 years, now happens twice every 10 years. So such a terrible thing, for example, might be a very devastating hurricane. Here's one that struck Mexico 4 years ago, Hurricane Maynard, right? And we cannot say whether, this one is due to climate change or not. These things happen, on average, once every 10 years. But if another one comes and Sandy hits us again, and before that there was Katrina, all within 10 years, then we can say it's very likely that one of them is normal and two of them are due to climate change. We just can't say which one. Right? Well, extreme events are important because they cause the most damage and death. Right? So we see this all over the world, right? That the storms are becoming more frequent. Now, so that's a physical phenomenon that everybody can understand. What about the biological phenomenon? This I worry about even more. Suppose you live or work at the CFA where it rains a lot. What happens when there's more rain than normal? Well, what happens, and this is happening, is that maple trees are now more susceptible to infection by fungus. How much more has this been? People have kept records. Maple trees give maple sugar. The sugar level in a normal year is 3% of the sap. Today, in a bad year, it's 1% of the sap. Imagine that. Suppose somebody tells you in your blood, you're supposed to have this thing at 3%, and they measure it, and it's 1%. You better go to the hospital, right? Problem is, there are no doctors in the hospital. All right, now here's something that happens on the west coast of the United States. Trees are dying. This is up in Canada, British Columbia. The pine trees are supposed to be green, evergreen, right? They are dying. They're being attacked by pine beetles. This phenomenon is not only happening on the west coast of Canada, it's happening throughout the west coast of the United States, all the way down to Canada, to where I live in San Diego. Why? Because they're being attacked by pine beetles. Why are they being attacked by pine beetles? because there's less rain than normal. So when the beetles come out in the spring and the summer, they look for water. Where's the water? It's in the trees. So they go and attack the trees for the water. Then comes winter, but it's too warm on average. So normally the winter would have killed most of the larvae. Now more larvae survive. So next time around, you have even more beetles. Okay? So this is probably behind this great pine beetle killing. How much is it per day? In 2 states alone, 100,000 trees fall every day. In Wyoming and Montana. It is very frightening. So you can ask, why hasn't it come down to Mexico? Well, here's a group that has studied this problem. I believe Morelia is out here, is that right? Yes. So, here, pine beetles here, all right? But it is not yet grown or evolved to be really killing your trees. Here are the most dangerous spots. You see, Morelia is in a band running east-west of the most dangerous regions. Okay? So we don't know. We hope that it won't happen here, but you should do some preparation. When it comes, it will be devastating. So people should be prepared. Is this only unique to the Americas? And the answer is no. There have been studies of 226 forest trees in 81 forests of the world, and 70% of these species are on the verge of death from water stress. 70% on the brink of death. Imagine that. What a catastrophe this is. People don't emphasize this enough. They say we can adapt. Humans adapt much less quickly than insects or fungus. There's no hope of adaptation if this really takes off. Okay, so let's try to understand fossil fuels a bit. Why do we have coal? Why do we have oil? Why do we have natural gas? The answer is because we have biomass. And in particular, 300, 400 million years ago, carbon dioxide levels were much higher than they are today. They've been sequestered by the following biological and geological process. These trees die, they either fall into the water or they get buried in the ground. Gradually, as they are pressed into the ground, because the earth, solid earth, is also like another blanket, but here it's radioactive heat trying to get out. As you press deeper and deeper, it gets hotter and hotter, and the biomass will have be transformed thermochemically into various forms of coal until it's almost completely carbonized. So coal is basically a complex mix of compounds that include carbon, hydrogen, and oxygen. Right? Now, why do we have oil? It is because sometimes you are in a region where there's lots of acids. Acids like to give away a proton or hydrogen. And that helps to eliminate the oxygen. Two very complex reactions that nobody understands very well. Our Glasgow should really study this problem. But that is the basic idea. So you get mixes of hydrocarbons, basically carbon plus hydrogen in various combinations. That is basically petroleum. Now if you press it even deeper, it becomes very high temperature, and then laws of thermodynamics tells us when the temperature becomes high, complex things like become simpler, more in number. So all the hydrocarbons become the simplest one, which is methane. Just one carbon, 4 hydrogen atoms. That is natural gas. Natural gas, basically 90% carbon. So this is a great bounty to us. However, it offers a climate threat. Because if burnt, these known reserves are 5 times as much as consistent with the survival of present civilization. 5 times. And why should we burn it? Because oil companies are very rich and very powerful, and they're intent on burning it all. So, why are they so rich? Why are they so powerful? It's because energy extracted from the ground is relatively cheap, and that's what's allowed us to have this great expansion in our economic wealth. So, if you study this problem, you will find an etude of reasons why it's very efficient. First, it's easy to extract oil. The energy return on energy invested, what people call EROI, is between 5 and 20. It used to be about 100 when people first discovered oil. But now we're extracting oil that's harder and harder to get out. And so now Saudi Arabian oil has about 20. And if you talk about Canadian tar sands, it's about 5. It's so viscous, it's hard to get it out of the ground. Now, it turns out economists have studied this problem. If you drop below 6, the world will go into a depression. So if we had to count on Canadian tar sands, we'll probably trigger another depression. It's only because we have better sources, such as in Mexico, Saudi Arabia, etc. But we're not already into that economic state. The second is that it's easy to transport. It's a liquid. We oil things, right, to produce sufficient. So it's very easy to pipe it. Once you get it to the ocean, you can even ship it across because you just pump it into a big tanker and you go. Canadian tar sand, not so easy. It's so viscous, it doesn't really work if you try to put it into a pipe all by itself. So you have to build 2 pipes. People don't talk about this. One pipe to pipe up light oil from the United States or from Mexico to Canada, mix it with the heavy oil so it becomes a lubricant, and then pipe it. That's why the pipeline companies love it. Right? You need 2 pipes, not just one going down. You need one going up. Is this smart? I leave it to yourself to judge whether you should be doing this. Second, you can upgrade. That is, light oils, like kerosene, you can use in airplanes because it won't freeze. Heavy oils, or medium oils, you use in automobiles. Heavy oils, you use in stationary applications such as home heating. So you can upgrade it by refining it, separating the heavy and light oils. And you can also transform them, making even more money by petrochemicals. Most of the chemical industry today is petrochemicals. It's easy to distribute. There's a vast network set up to do this. There's an established infrastructure. Finally, it's easy to store. So you can store it, use it when you want. Chemical energy is much better than electrical energy in that way. It's very hard to store electrical energy, but very easy to store chemical energy. So what do I mean by this? Quantitatively, 1 liter of gasoline, everybody has an idea of roughly how far you can drive with 1 liter of gasoline, has the same energy content as 8 liters of lithium-ion battery. Usually we don't measure battery in those sense, but we're worried about volume. It's about 8 liters of lithium-ion battery. 1 liter of gasoline will cost you about $1 per liter, right? $1 US. 8 liters of lithium-ion battery will cost you about $8,000. Now, of course, you can charge this 1,000 times, and then you have to throw it away. But I can also buy 1,000 liters of gasoline, and it's only $1,000. So I'm still better off by 8K, by a factor of 8, even though we haven't counted the charge of the electricity that's needed to charge. I'm not telling you this to praise so much oil and gasoline, but to tell you the difficulties. When you think that you want to build electric cars to replace the current cars we have today, what the difficulties are. It's not an easy matter. Okay, now we say, well, we're doing lots of an R&D to push these numbers down. Well, don't think the opposition is standing still. They also have their innovations. They say, if the oil's like this, why are we drilling here, here, here? We should go over here and then drill horizontally. That is a big advance in drilling for oil. To get natural gas, well, there's a pocket here. If I drill here and I suck up all the natural gas, that's it. But if I crack the rock, if they crack the rock by injecting hydraulic fluids down there and crack the rock, then the pool over here can reach over here and you can extract it. They say it can be done safely. I believe it can be done safely, but not by everybody. Somebody will cut corners to try to do it too cheaply, and then we will all pay the price, because methane is a much worse greenhouse gas than carbon dioxide. Now, shale gas is very cheap. Why is it cheap? Why is it so cheap? It doesn't look like it's very cheap. It's cheap because it's difficult to liquefy and ship. as a gas, it's much, for the same amount of heating power, it's occupied much bigger volumes than oil. So if you try to build a pipeline, the pipeline will be huge. So it's not profitable to ship it by pipeline. It's only profitable to ship it if you can liquefy it and then ship it. But to liquefy methane, you have to get to very low temperatures, very high pressures. It's very expensive. Nevertheless, they're going to try to do this. Why? Because liquefied natural gas in Taiwan or in Japan or in China costs 6 times what it does in the United States. So they're going to do it. And when they do it, it's also going to become a world market, and then it will no longer be cheap locally. This is not what they will tell you, but this is, I think, the likely scenario if we rely on shale gas. It's cheap today only because they're overproducing it locally. They cannot ship it, so they overproduce locally, so they have to sell at bargain basement prices. That's not going to be true if they get their way. So let's look at the history of world energy generation to see the trends. At the beginning of the 20th century, you can see that just burning wood and other bioenergy sources was more than half, provided more than half of the world's energy. Coal provided almost the rest, and we're just beginning to use oil and natural gas. Today, of course, oil has expanded tremendously. Natural gas is expanded tremendously and even more into the future, so that they now account for more than 80% of total energy use. The other two things that have expanded quite a bit is nuclear power, despite all its problems. Hydroelectric has not, because basically we banned all the rivers in the world, but it's possible to ban. It's a technology of the 20th century. We can't expect to continue to expand it into the 21st century. And then bioenergy. Here are all the other renewables that people talk about. It is tiny little slivers. So despite the heroic levels of investments, wind and solar, which is in here, and it's not even the major part, the major part is geothermal, are not displacing fossil fuels 40 years after the first oil crisis. The first oil crisis was in 1973. Moreover, wind and solar are intermittent. The sun is down at night. You cannot count on electricity. It's not overhead all the time, even when it's overhead. Sometimes it's cloudy. It's a wonderful source. I love it. How can an astronomer not love solar? But we have to face reality. If it gets cloudy today, are you going to stop using your laptop? I don't think so. When the wind doesn't blow, are you not going to cook? I don't think so. So you have to back it up. And what's being backed up when it doesn't blow today are natural gas plants that are just spinning idly. When these things go down, they quickly surge the electricity into the grid. So if you build more wind and solar, yes, it will decrease the total amount of energy used, but it will also increase the total amount of natural gas used. And although natural gas, because it only has one carbon, or hydrogen is better than burning coal, it's still emission-free. It's about half of coal. So in my analysis of this situation, personally, I think realistically, given how long it takes to develop any of these technologies, you have to count on 50, 60, 70 years of development. We don't have the time. We need to make what we have better. So first, we must make fossil fuels cleaner by carbon capture and sequestration. People who don't know what this is, you can ask. I will explain it later. Bioenergy at scale without subsidies. You have to be able to compete economically, in my view, with these other companies, because they're so powerful. And third, we have to make nuclear safer, more affordable, with a solution for the waste. So let me tell you the simplest way to get the energy out of a biosystem. We should learn from nature. That is, don't try to do it biologically, which everybody else, many other people are doing. That's too slow. That's room temperature chemistry. Nothing goes fast at room temperature. You have to get the high temperature. That's what nature taught us about fossil fuels. So we can't use water. It only gets 100 degrees. We would like to use a liquid, so we use salt. Okay? In particular, in these experiments that I'll tell you about, We use 300-degree molten salt. This is sodium acetate, potassium acetate. It's very safe salt. It's what's used to flavor salt and vinegar potato chips. This has no problem. If we have a bucket of it and we just dump biomass in there, being under the surface of the molten salt automatically excludes air, so it becomes something very similar to coal. We basically char it. We make charcoal in 10 minutes. What nature takes hundreds of millions of years doing, we can do in 10 minutes. It's not quite as dense because we don't have the pressure, but it's dense enough. Now it's covered with salt, so you bring it to this bucket to wash it. Salt's easily soluble in water. If it's not clean enough for you, you wash it again, and then you bring it out. So you put it in here, you crank it. We call this a crankberry. Right? We designed it with the idea that children should be able to understand how this works. So through these bicycle chains, right? You transfer a cylinder of biomass with holes in it into the molten salt and make biochar, right? Make charcoal. Charcoal is the oldest technology in the world. Probably discovered at the same time the fire was discovered. You just need incomplete combustion, you'll get charcoal. So what is the EROI we think we can make this charcoal at? It's about 30. So we think we're not going to throw the world into depression if we pursue this in large scale. So what can you do with the charcoal? Of course, one thing you can do is to replace coal. Instead of using coal, you can burn the charcoal, which, because it comes from a renewable source, the plants extracted the carbon dioxide, you put it back, but next year's plant makes it carbon neutral. You can make coal-fired power plants carbon neutral. In fact, we like another idea better. You can bury it as biochar to offset the burning of petroleum-based fuels. So what is that idea? The idea is we shouldn't have been digging out coal out of the ground and burning it all these centuries, all right? We've done that, we made that mistake, there's no point crying about it. Now we should reverse the process. We should make coal and put it back into the ground, as much as we've dug out, or more if need be. So that's the idea. And this is the design that we've come up with, and with help of this CSISD, as I said. So this is made to be transportable. We want to go where the biomass is, let's say mountains. So we'll take it up to the mountains where the biomass are. The biomass is brought here, funneled into a basket, which is rectangular in form, so space filling later. It's porous, all right, and you put it into a heater where you have molten salt. After 10 minutes, you transfer it over. Actually, here we have both a pre-drying and a preheating step. Then you put it over here. You need to wash it. So you put it into here. It moves slowly up this way. On this side, we have water, which flows from here to here. So you have fresh water flowing this way. You have salty charcoal. You go this way. As it meets the water, it becomes less and less salty. So by the time it's out here, you've recovered all the salt. You lift it up. You put it into a truck that takes it to wherever it's destined. The water becomes, as it flows through the salty charcoal, becomes saltier and saltier. And over here, you have saturated water with salt. And so we put it into the heater, drive out the water, and then you separated the salt and the water, and then the water is put over here. So in fact, we're a source of water. We're not a consumer of water, because all biomass has water. We recover that water. Now, in addition, you can see over here, there's a bubbler where we condense the volatiles that are driven out by the process. Among these volatiles are acetic acid, vinegar, which we can convert, I won't tell you how, but it's a very simple step, to convert it to acetone, which is a feedstock for transport fuel. Things that you cannot condense bubbles out, and is also a fuel. We call it syngas. Why is that? Because we have things that are carbon, hydrogen, and oxygen, has a lot of water, has a lot of carbon. And at high temperatures, you can actually burn carbon with water. Don't burn it with oxygen. Burn it with water, and then you can get this reaction to go, called water shift reaction. You get carbon monoxide, which is burnable, and you get hydrogen. And that would hope to replace natural gas. In fact, this was used in the 19th century. People lit street lamps with it. They cooked with it. It's called pan gas or coal gas. Sometimes this is what people mean by coal gasification. So we have to return back to that rather than burning it. Something that is renewable. Okay, so let me show you some results of things that we've torrefied in that crankberry. Bamboo is the fastest growing plant in the world. It is a land plant. It's abundantly available in Asia, so we study it. So you put a big piece of bamboo and it becomes charred. Okay? You cut it up, it becomes equal to charred. So that's a great advantage. The salt actually penetrates into there. So big pieces and little pieces within reason cook at about the same rate, and we make nice black charcoal. Chinese eat with disposable chopsticks. Lots of Asian countries do. So after you finish eating it, don't throw it away. Let it decay or bury it in landfills. Make charcoal out of it. Toothpicks, make charcoal out of it. Lucana, this is something that's I'll shortly talk about. It's a bush. It's a bush that grows in Taiwan, and it becomes charcoal. Orange peel, charcoal. Banana peel, charcoal. Grapefruit rind, charcoal. So you can do anything as long as it basically has an organic origin. I like to say to astronomers, we found a way so we can turn all forms of ordinary matter into dark matter. That's what we need to do. And we should start with these things like this. Susanna told me Morelia doesn't separate its garbage, but Mexico City does. Okay, don't throw that stuff away. You know, retrieve what you can use, and otherwise make charcoal out of it. Okay? Charcoal does not rot. It is not like banana peel. You throw it away. After a week, it's all rotten. You will have released carbon dioxide in that thing. Charcoal does not rot. Right? You can have a bag of charcoal in your garage for 1,000 years. It will not rot. You've sequestered it. Okay, now Lucana is in fact native to Mexico. So how did it end up in Taiwan? I don't know what you call this in Spanish. It's a mimosa-like plant. I have it in San Diego in my garden. It's native to Mexico. It has a tremendous quality. It grows in very poor soils, and it's nitrogen-based. So you don't need to add chemical fertilizer. It grabs nitrogen out of the air, and it fixes the nitrogen. It was introduced to Southeast Asia by the Japanese, in particular on this island called Tahiti, which in Portuguese is called Pescadores. It's now overrun 70% of the island. Here's a picture taken by Taiwan EPA. Why is this? Well, pescadores, which means fishermen. This island is on the path to the Polynesian migration. They came here before they came to Taiwan. And for thousands of years, they fished for a living because the soil was so poor, only grass could grow, no big trees. And so if you have to catch fish and you have no wood to burn with, what do you burn? You burn cow dung. It's a terrible thing to burn. So the Japanese, when they occupied Taiwan, introduced this thing. Now you burn wood. That's much better than burning cow dung. But today, everybody uses natural gas or propane. So this thing has been neglected. It's overrun the island. 70% of the top land area is overrun. It's an invasive species that threatens to crowd out everything else. Okay? The Taiwan EPA came to us and said, can we help? I said, yes, we'll make charcoal out of this. So we made charcoal, and here's the assay of the qualities of this charcoal compared to what Taiwan Power Company, or Tai Power in short, paid last year to 5 tenders. First, what's the heating value? Every kilogram yields about 21 megajoules. Ours is 23, so it's better per kilogram. How much sulfur is there? Sulfur's terrible. When you burn coal, you release sulfur dioxide, gets into the water, becomes sulfuric acid, it acidifies the oceans. That's a huge problem. So the EPA of every country will want you to reduce this by at least a factor of 10. Well, we didn't dig this out of the ground. It's in plants. Plants don't pick up that much sulfur. So even without any abatement, it already satisfies EPA regulations, more than a factor of 10 lower than that. Here you have ash. What kind of ash is this? Well, you've dug things out of the ground. So in addition to the coal, there must be little pieces of rock and stone in coal. In those little pieces of rock and stone are metals, heavy metals. Some of them are volatile, such as mercury, lead. So when you burn coal, all that stuff ends up in the environment, right? Settles down somewhere, and this is why people are getting sicker and sicker. Why the rates of cancer are going up everywhere in the world. Terrible thing that burns. Well, we have ash. That's what plants take up. Plants don't take up mercury and lead. So what is left when you burn this is called potash. Those of you who know English know potash is conventionally given to that kind of ash, which was burned in pots. People deliberately did so because it gives you potassium, which is a necessary plant ingredient. So this is not waste, this is fertilizer. Now, there's another thing which is called the Hargrove grindability index. Greater than 45 becomes acceptable. Basically, the way we use coal today is really frightening. You grind it up into a powder, you spray it into a furnace. Has so much area, it immediately ignites into a fireball, and that's how we burn coal so fast to provide the power that we need. So you have to be grindable, and this refers to what percentage goes through a standard sieve. So if greater than 45 is acceptable, ours is 67, easily grindable. So in every respect, it is better than natural coal. In particular, the price that was paid by Thai Power was this last year. We think we can make it pretty much all over the world. Obviously, it will be fluctuation under $70 a ton. We want to beat them by a healthy margin so people will stop using coal eventually. So, you see this table, you'll say, well, it's a no-brainer, right? People should do it. No, because you have government, you have all these. We applied for a grant to help to turn what's a waste into a resource so that they can make money. We're not allowed to make money, so anything different between what you sell for and what you can make it for, profit for somebody, presumably the local government, and the people, would think this is a great thing. No, we applied for a grant and we turned down. They did not want us to do this demonstration project. Why? Because the Council of Agriculture said you should not use this invasive species. You should eradicate it. We said, well, it's invaded many parts of the world. Nobody has succeeded in eradicating this plant once it's become established. So you better make, an omelet out of this broken eggs. Because its roots are very deep and it has seeds. These things become seeds, they drop into the soil. They live for 10 years or more. You have to get every single seed out of the ground. You have to dig it up by its roots, or you try to kill it. And that's what local farmers do. They pour diesel oil into the soil to kill it. What we're doing is worse than that. Doesn't matter, they don't listen. Especially because the EPA suggested that we should help, right? They didn't. So, and Thai Power doesn't like it. What's their reason? They say, this ash we use it. We give it to concrete companies that mix it with the concrete, and it becomes trapped in the concrete. If we mix your potash in, maybe the concrete companies won't accept it. So they don't like it. I mean, you have to face these realities when one tries to push this. Nonetheless, we're not discouraged. We're going to go to private investors. I tell Thai Power, you have to be honest. What is your business? It's burning coal, isn't it? It's not making concrete. But that's the way people think. I'm going to counter this kind of thing. So here's how you can use it as a soil net. Rather than burning it, you can add it to the soil. Now, where would you add it? For example, here is an abandoned silver mine in Colorado. Now, where you mine silver, silver has associated things that you don't take away. Arsenic, mercury, cadmium, zinc. Except for this is awful stuff, bad in the ground. So this mine was abandoned 100 years ago, and nothing can grow, all right, in the tailings. For 100 years, it looked like this. And then in 2010, people in Colorado got a good idea. They said, we have all these trees that have been killed by pine beetle. Let's make them into charcoal and put it into here. Why? Because charcoal is a good soil amendment. How good? Well, after 1 year, it looked like this. Why? That's what I can tell you. Anyway, they used conventional technology, which you could take up into the mountains, basically uses gases to transfer the heat. We're 2,000 times better than that, but by the time I can recover salt, maybe only 200 times better. So what they can produce at 0.23 tons per day, we can do at 59 tons per day biochar. So each year, if you count 360 days a year, 5 days, we'll transport to another site and set up again. Each year, we would make 21,200 tons per a year. If you say per hectare, we're going to bury 100 tons of it, then that's 212 hectares that you would turn from looking like this to this every year. What is that? That is one UNAM campus every 4 years. I'm talking about all the campuses. How much is UNAM worth to Mexico? A lot more than burning this, right? You shouldn't burn this. This is too precious. You should burn it, you should bury it, and recover damage. How much damage is there? There's an opportunity for Mexico. Mexico is the largest producer of silver in the world, at least in 2010 it was. So there must be many sites like this that could benefit from this kind of treatment. Why is biochar so effective? Well, think about it. First of all, here's an electron microscope scan of what happens if we take leukemia and heat it up to 300 degrees for 10 minutes, okay? Basically, you don't, the cell walls remain intact, but the stuff inside the cell walls are also there. It's okay, it's good enough for if you're going to burn it. So we call this use eco-coal. If you take it to 500 degrees, so you clean out everything inside the cell walls. Everything that's left is just cell walls. 500 degrees for 11 minutes. Now this is very porous, more porous than the interstellar medium perhaps. How do they measure porosity? The experts use a method called BET, Brownell-Emmett Teller. How much area is there per gram? Okay? The answer is, if I have 1 gram of this charcoal, I can hold it in my finger. The surface area of that 1 gram of charcoal is the surface area of this ceiling. That means a tremendous sponge. So when it rains, all right, what will happen is that the water will get trapped in these pores. When it dries out, the water will come back out because it just goes in the direction of the osmotic pressure. So it's a great way to store water. When it's raining, it goes in. When it becomes dry, it comes out. So you need less water to grow the same plants. Moreover, when it rains, it carries these toxins inside, this maize, and they get trapped. So they are filtered out, and when the water comes out, it's nice and clean. We've seen this. We can wash it with dirty water. Because the dirty water becomes cleaner by washing the charcoal. So that's it. It's obvious. What do we do to get clean water? We filter it through charcoal, right? We just have a method of producing very cheaply lots of charcoal. Water is going to be the second great problem in the 21st century after energy. So we think this is a much better use than we would hope that people would use it. Nevertheless, transportation fuel. How do you make transportation fuel? Well, here's a suggestion from Mexico. Biodiesel from used vegetable oil. Your cuisine uses a lot of vegetable oil, but you're not making good use of that vegetable oil when you're through with it. Mexico, I'm sure you use more than 0.003 liters per year per person, okay? But this is all the biodiesel you're producing from it. You should not regard this as a waste. You should regard it as a resource. So how do you use it in principle? After you cook with it and it becomes too dirty to continue to use, you collect it, you filter out the particulates. You pour methanol. What's that? That's wood alcohol. That's the other thing that we get besides acetic acid. Plus methyl acetate, you get that too, and hydroxides, sodium hydroxide, potassium iodide. Pour that into the warm oil after you filtered it, and it will react. Right? This will act as a catalyst to so-called transesterify the vegetable oil into biodiesel. There's a waste product, which is called crude glycerol. Glycerol is a pure, valuable commodity, but because it contains all that hydroxide, people regard it as a waste. They have to pay people to haul it away. But we know how to take this crude glycerol, gasify it for fuel as circulatory action. That's one way how we bring down the price. We're left with the hydroxide, which we can easily make a salt. In fact, we choose a salt substitute because of this connection. So there's no waste. What's left are fatty acid methyl esters, called FAME in Europe. So you wash the FAME with water, so it has contaminants in it. Oil and water don't mix, but the water carries all the contaminants to the bottom to drain it out, and that is biodiesel. You filter once more, right? And now you can store it, you can distribute it, using the same system that's already in place. Mexico has spent many, many billions of dollars each year setting up the system. You don't want to knock those down, you just want to replace the fuel. So biodiesel, I believe, is 100% usable in Mexico. You can't use it in jets that get too cold, it will freeze up on you. But Mexico is fortunately a country which I don't think it ever freezes at ground level. So you can use it 100%, not like ethanol. Last year, the government committed to binding carbon dioxide targets. I believe you're the second country in the world to do so. Reduced by 30% the carbon dioxide emission by 2020, reduced by 50% in 2050. I think this is very ambitious. I think this is far too conservative. You should be more ambitious. Okay? But nevertheless, the fact is that such a resolution did pass your Senate, and the vote was 78-0. That, I was very moved to see that Mexicans had this resolve to contribute to this problem. In the United States, we would be 0-0 because the Republicans were filibustering. So, what is your statistics? Well, your population is 11th in the world. Your GDP is right about where it should be, but you can improve. Oil production, you used to be second in the world after the US. It's now peaked, and you're now about sixth in the world. Still better than most countries. Your greenhouse gas emission is 15th in the world. So better. You emit less than your population. And the reason is because, of course, you don't burn all this oil. You export it for others to burn. So how do you get this 30%? I think it's very easy. If you just take 15, if you ask what is your greenhouse gas emission mostly from, 15% of it comes from clearing and thinning forests. So if you take that forest product and did not burn it, but instead made it into charcoal, which you then bury, then that's negative 15%. So in total, that's 30%, right? You would be right there. You just turn it all into charcoal. Why would you do this? Well, and how could you afford to do it? Well, first of all, what do you do with the oil that you don't burn? You have to find some way to use it. Otherwise, you'll be opposed by the oil companies. I'll just remind you that oil, if you don't burn it, is a wonderful substance. It can, as long as you make durable goods out of it, it is not putting carbon dioxide in the atmosphere. What are some of these durable goods? Well, of course, everybody's familiar with plastics, but people are less familiar with carbon fibers, except radio astronomers know this. People ride carbon bicycles or play with carbon tennis rackets. Carbon fibers come from pyrolyzing nylon. So I've gone to these factories, they're our partners. So nylon you can make into a long fiber, and if you just heat it up, you can drive out the hydrogen and the oxygen, and you get pure carbon. It's very weak at that point, but if you now heat it up beyond 900 C to 2800 C and above, it becomes graphite. And graphite has so many bonds that it's stronger than steel. So now you've got a rope of something that's flexible and stronger than steel. I'm sure all the ladies know, and some of the men should know, that from such threads you can make fabric. So once you have a fabric, you can make many things. You can make airplanes. You can make nuclear reactors. This is an airplane that Boeing makes completely out of carbon composite, except for the battery. It's called the 787. Why? Because it's as strong as steel, but much lighter, and therefore you save on airplane fuel, right? Which is a major thing that creates problems for airplane companies today. Many of you know this airplane has been grounded, not because the airplane is so bad, but those lithium-ion batteries are no good. Okay? So here's something that we made out of graphitic materials and carbon composites at the end. I can't say this in a US audience, it's a heat exchanger. But I would just point out that the core of a nuclear reactor is one of its functions is a heat exchanger. We're not going to try to do nuclear reactions in Taiwan and try to find international partners to do this. It exists in the telescope assembly building. We got Siemens, which is the biggest company in the world, to work with us, small fry, because they think that there's potential here. So let me try to finish and give the take-home messages, okay? First, climate change is real and it's here. Mexico's emission targets are commendable, but you need regulation to enforce the change. You have to say no waste. If you have waste, you must turn it into a resource or let somebody else turn it into a resource. The other thing I would comment on is that solutions often become problems. There are no problems that are solved forever. All human problems are only temporary. Right? Fossil fuels were great. They eliminated things like slavery, but they became a problem. Japanese introduction of volcano to Taiwan was great until it became invasive. Right? So don't try to find problems that are perfect. Do not let the perfect become the enemy of the good. Every generation has to solve its own problem. Do not demonize fossil fuels. There are very good reasons. You have to understand why oil is so pervasive in modern civilization. But we must find ways to coexist it. We don't want to put them out of business. We want them to go into another business. And we think this business of opportunity, here's a suggestion, if somebody burns a ton of oil, to become carbon neutral, they should bury a ton of biochar. If I bury the biochar and not burn it, who's going to pay for it? Not the utility company. The oil company should pay for it. So Pemex oil, because coal is only a tenth the price of oil, could add a 10% surcharge on Pemex oil. All right? That would be nothing. I think many of us would willingly pay 10% extra for gasoline that was carbon neutral. Now you pass, Mexico doesn't even have to pay for it, because you pass this on to the world, because Pemex oil is now carbon neutral. So you should be able to charge a premium for it. Why should the world pay for it? The world should pay for it because when you bury that ton of biochar, everybody benefits because it's moved carbon dioxide from the atmosphere, which we all share. So gradually, I'm sure if you do this first, and it's successful, other oil companies will follow suit, hopefully. But that's exactly what we want. So eventually, we would hope to transform to an economy that does not burn oil or makes durable goods out of it. Right? That's what we would hope. It's a path that people could compromise. So let me just finish by wishing Kriya a very happy birthday. And birthdays, one is supposed to give some present. Louise, many years ago, you gave me a wonderful present. Susanna Lozano as my graduate student. I have a very small present for you. It is what I could bring in the suitcase. It is a tie from Academia Sinica to symbolize the good ties that Mexico has had with astronomers and HI. I should also point out that character means king. So you have a pope who's the pope of IAU, and now we have a king of astronomy.
I have a question.
Excuse me, Doctor. What do you think of use of soil to produce fuel, like Brazil does, for example, with the sugarcane, or
As the States does with corn and some other.
So what's important is to look at the EROI, all right? If you look at corn ethanol in the United States, people argue whether it's above 1 or less than 1. Remember, I said you have to be above 6 without throwing the world into bad financial shape. Brazilian sugarcane ethanol is much better. It's about 8.3, okay? Soil, beans, I don't know, okay? I think because it's a legume, could potentially be very good because it's nitrogen fixing. It's a very good source of oil. So yes, but one has to look at the EROI. What many people don't realize about biomass is that if you have to cultivate it and you have to use fertilizer, it's a huge hit on the EROI because the way we add nitrogen is to add ammonia. How is that ammonia made? It is made from petroleum. You have not only nitrogen, you have hydrogen. That's the reason why these plants can grow so fast. They're not only getting hydrogen out of water from photosynthesis, they're getting it out of the soil. So that is a huge hit if you have to use cultivated land. We should not be using land that we can grow food out of. But poor soils, yes, that's fine. But poor soils, by definition, for most plants, mean you have to add fertilizer. That's why we chose Lucana.
Thank you very much. You say the cost of making 1 ton of biochar is roughly $70 per ton, right? In this number, how much is the cost of the biomass?
The 3 main things are biomass, that's most. We're planning to pay $40 a ton.
$40.
Yeah.
Okay.
Next is salaries, because you have to have a minimum number of people just to operate this machinery safely.
Exactly.
Okay. Next is the fuel. Because what you would optimally like to do is to burn some fraction, 1/30 of the biocoal that you make to power, the heat for the molten salt. But burning coal is you get particulate emissions. So usually that's a big problem unless you have a huge coal-fired power plant. So we want to use something that's basically gaseous. If we were to use natural gas in Taiwan, I already told you, 6 times what natural gas is in the United States. So we instead hope to partner with biodiesel fuel. So we take their waste product, gasify it into something that we use as a substitute instead of natural gas. So those are the 3 most expensive. The equipment is almost nothing. So, we're not going to make lots of money. We don't want to make lots of, well, I shouldn't say that. We're not going to make lots of money. We think the people who should make the money are the people, in the rural areas that actually make these products out of waste resources.
Okay, and burning the syngas produced from the carbonization?
That produces water and carbon dioxide. So, but that was originally in the plant. So if you just let the plant rot, it would have gone back without us getting any benefits. So syngas, as I said, is an old technology. It was what people used to use before they started burning natural gas. There was a movie made called Gaslight. You may remember it, Jim, where Charles Boyer tried to poison Ingrid Bergman. He was poisoning her with carbon monoxide. Okay. Anyway, it used to be used, so it's.
You had said that you had a portable prototype of this torrefactor.
Yes.
that could be carried to rural areas. So that also works with biodiesel. That's the, how do you,
Oh,
There's
so
no-
why is
there's
it
no
even 1 in
electricity.
30, right? Why isn't it infinite? It's because we're planning to use normal diesel. So that's the input. Okay. Things like that. In principle, eventually it can become completely self-contained. Yeah.
Okay.
But right now, Taiwan has biodiesel, but Mexico really doesn't.